Okay, so in this video we're going to go over limits and continuity in AP Calculus AB/BC, um, which is kind of the same thing. BC just goes over the entire calculus concept, whereas AB goes over like half of it, but they both go over limits and continuity first. So let's say we have this really basic function, right? F of x equals x plus 5, and we want to find out the limit of as x approaches 3 of f of x. Now, if you don't know what a limit is, so a limit is basically describing the graph's behavior as it approaches like a certain value. So for example, this is like, this is 5, right? This is the y-intercept, as you can tell in this equation. Yeah, plus 5 right here after x, and that is indicative of your y-intercept. So the limit notation for that would be as lim x approaches 5, or no, as lim x approaches 0, because 5 is the y-intercept, my bad, f of x approaches 5. It's kind of like limit notations are like the end behavior of a graph, except we're exploring it in greater detail within the domain. We're not talking about like as x approaches infinity or negative infinity anymore. We're talking about actual numbers that are within the graph. So, with that being said, using this graph, what would the limit notation be as x approaches 3? Well, I didn't put any labels on this graph, but you can actually figure this out using the equation itself. So when f of x, so f of 1 is 6, f of 2 is 7, and f of 3 is 8, which f of 3 is going to be like right there. That's f of 3. This coordinate would be 3, 8. And we're talking about the limit notation. So as x gets closer to 3, it's getting closer to the y value of 8. That would be your answer. So let's say we have this graph. Let's say on one side we have this. On the other side, hold on. On this side, we have this. Let's say this point is like -1. Now we want to find the limit notation as x approaches 1 of f of x. But as negative, for -1, not +1. So the first thing you're gonna realize here is that this is a bit confusing, because on one side we have -1 approaching the y value of, seems like 1, I guess you could say 1, and up here you have as x approaches -1, it's approaching the y value of like, say about 5-ish, 5, 6-ish. This is where we're introduced to positive and negative limit notations. On one hand, we have as x approaches -1 from the negative side. So in other words, that means from the left side. So as we're approaching from the left side, we're going up here. F of x equals, say, about 5-ish. This graph isn't very defined, so we're just going to say that. Whereas on the other hand, we have lim x -1 from the positive side. From this side, f of x would equal 1-ish. That's basically the difference between negative and plus, negative and positive limit notation. So when it's asking you to find the limit notation of as x approaches -1 from the negative side, it's asking like where the graph is going from the left side. So like up here, the graph is going to 5, the y value 5 as it approaches -1. Whereas as x approaches -1 from the positive side, from this side, it's approaching around 1-ish. That's pretty much the difference. There's 3 rules of limits. Well, actually, there's 2. One, these two must be equal. The limit for limits to exist, the limit as x approaches c from the negative side has to equal the limit as x approaches c from the positive side. They have to be equal to each other. And the second rule is that these limits cannot equal plus or minus infinity, because that would mean that we have a vertical asymptote, and vertical asymptotes invalidate limitations. So using the graph we have right here, I want you guys to pause this video and find the limit notations of these 3 functions. Problem 1, problem 2, problem 3. Okay, I'm going to solve it anyway. So for problem number 1, for the limit notation as x approaches -4 from the negative side of f of x, that equals negative infinity, as you can see, right? Because as it's approaching from the negative side, it's going to negative infinity, right? Seems pretty simple. For this problem, as the limit as x approaches 1, I know it shows that there's a hole here, but here's the thing: limits exist when the limit notation from the negative side and positive side are equal to each other, and in this case they are. So regardless if there's a hole or not, they're still equal. So this would be 1, because it's connected to 1 right here, as you can see. I didn't label it too well, but that's that. And then for the last problem, as x approaches 3 of f of x, this does not exist, because from the negative side, we're going down to like a negative number. I didn't label the y values here and here because you should already know that the limit here does not exist, because they're approaching two different values. It doesn't matter which one is the whole and which one is the actual value. We're describing the limits, not f of 3. So from the negative side, it's going to a negative y value. From the positive side, it's going to a positive y value. So this does not exist. Now let's try the substitution method in limitations. We're going to go over 3 methods today: substitution, factoring, and conjugate for limitations. So let's say for this one we have, as x approaches 4, we have this equation. We want to find the limit as x approaches 4 of this function of x squared minus x plus 2. What you can do here, you can literally just plug it in. You have this 16 minus 4 plus 2. 16 minus 4 is 12, plus 2 is 14. So this would equal 14. So it's pretty simple here. The substitution method just basically says that you just plug in the x value, which is 4, and then you just plug it into this function right here, because you can just solve it that way. Now let's try it on your own. So you can pause the video here using the substitution method that I just taught you, try to solve these two on your own. Remember, you just plug in the value of x, these two, into the equation. Okay, so in case you didn't do this, for the first one, you just have to plug this in to x. Cosine of pi is just -1, and then you have -1 over pi. And then when you simplify that, you have -0.318. That's your answer for the first one. For the second one, you just plug in -2 into these ones. 2 squared is 4. 4 plus 1. 4 minus 1. Then you have 5 over 3. That would be your answer, 5/3. Seems easy so far, huh? Let's go over the more difficult stuff. I want you to pause this video and use the substitution method to find out what this value, what the limit will equal as x approaches -3. If you already have, you'll find that you'll get 0 over 0. And that is not the answer we want. I keep forgetting to switch colors sometimes. So this introduces us to a new method called the factoring method, which goes a little like this. You're pretty much just, this is going back to lower level math relative to calculus students. This cancels out. You now have x minus 3. Now you plug in -3. You get -6. -6 is your limit notation. That's basically what the factoring method is saying. For some questions, you can't really substitute the number directly into the function as it is, because you still have to factor it a little bit. I want you to pause this video and solve these two problems using the factoring method that I just taught you. Okay, let's solve this. So, first off, in this first problem, we need to factor this out. Let's put that to the side. 2x squared -15. Factor it out, you get 3x minus 10x. 2x here, 2x here, 3, -5. The -5's cancel out, so you're just left with 2x plus 3. You just plug in 5. 2 times 5 is 10, plus 3 is 13. So you have 13 as your answer. Now for this problem, again, you have to factor this out. You end up with x plus 1, x minus 1. The x minus 1's cancel out. You're just left with x plus 1. 1 plus 1 is 2. Now, here's the last method that you would have to use for limits. This is called the conjugate method. So before we delve deeper into this, I want to walk you through this. So if you plug in 5 immediately, you get 5 plus 11, which is 16. Square root of that is 4. That equals to 0. 5 minus 5 is 0. That gets us 0, 0. And that is not what we want at all. So you want to avoid this at all costs. But we don't really know too well how to factor this. Or maybe you do, but there's just a better way to do it. That's by multiplying this function. Oh, my pen's not working. Okay. Multiplying this function by its conjugate. So x plus 11 plus 4. X plus 11 plus 4. Do that on both sides. The square roots cancel out. This becomes -16. You have x plus 11 minus 16. That gets you x minus 5. You don't need to multiply these two out. you just have x minus 5 times square root of x plus 11 plus 4. These two cancel out, so you're just left with 1 over x, square root of x plus 11 plus 4. If you plug in 5 now, 5 plus 11, 16, square root of 16 is 4. You end up with 1/8, which is not 0 over 0. It's not a big number. It's not the most exciting number, but still better than a 0, 0. I want you to pause this video and try these two problems on your own using the conjugate method that I just taught you. Okay. So for this problem, pretty simple. If you plug in -2 immediately, it's not going to work, and so won't my pen. But if you multiply them out by their conjugates, you get let's see, on the denominator you get x plus 6 minus 4, end up with x plus 2. These two cancel out, and you're left with the conjugate itself. Plug in -2, -2 plus 6 is 4, square root of 4 is 2, plus 2 is 4. For this one is a little tricky, because realize that when you plug in 1, you get 1 plus 4, square root of 5 minus 3, and then you get square root of 5 minus 3 plus 2. Believe it or not, this is the answer. The main key when simplifying, when evaluating limits, is to not get this answer. We don't want 0 over 0. That's just pretty much the only goal. If you end up with a weird wonky answer like this, that's completely fine. Still better than a 0 out of 0. Okay, now let's go over continuity. Okay, so there's 3 rules of continuity. Oh, by the way, continuity, you can think of it as like a wire that is not broken anywhere. You see how like it's still connected, it's all connected, it's very stable. What would not be continuous is if we have a hole in between. What's also not continuous is if we have an actual value down here. And what's also not continuous is if you have like, this is called jump discontinuity, which I'll delve into greater detail later on. But this is basically what jump discontinuity is. Anyways, the 3 rules of continuity. First, the limit of as x approaches c of f of x must exist. It has to exist. 2, f of c is defined. And 3, the limit of as x approaches c of f of x is equal to f of c. These are the 3 rules of continuity. If all 3 of these are met, then that makes a function continuous. Okay, I want you to pause this video, and I want you to determine whether or not this function is continuous at x equals 1. Okay. So if you plug this in, well, you don't need to do anything at the bottom here, because it's already given that x equals 1 is -2. Here, however, it's a little bit bad. Here, however, you need to actually plug 1 into the equation. So when you plug 1 to x, you end up with 3 times 1 squared, which is just 3, minus 1, which is 2, minus 2, which is 0, well, you end up undefined. So you have to factor this out. The reason why is because it's 0, 0, and we don't want that. So, factor it out. Sorry, I'm drawing with my finger right now. My pen is dead. Okay. You have your little diagram here. 2x minus 3x. 3x up here. X up here. Negative 1 up here. 2. The negative 1's cancel out. You're just left with 3x plus 2. Plug in 1. 3 plus 2, which is just 5. So this is not continuous. Because the two values are different. For these to be continuous, our y value would have to equal -2 for this equation instead of 5. And these two are unequal. So that would not be continuous. So one that I just went over, we have jump discontinuity, which is basically like this. This is supposed to be a filled in point, like that. I mean, this is kind of ugly, but it's okay. Bear with me. So what jump discontinuity is basically saying is that on one side, you're coming all the way down right here. This is the actual value. When we plug it into our calculator, this is the value you would get, which is up here. But at that same x value, it's basically as if you're like jumping right down or jumping right up. That's why they call it jump discontinuity, because there's two different points. This is a hole, and this is not this would not be our y value here would not be defined at this value. And this is already discontinuous because the limitation of C, let's just call this C, does not exist, which means it's not continuous. So we're done. So we already know that automatically. So that's what jump discontinuity is. Then there's point discontinuity, which is basically this. Basically, when there's a hole. And that's what makes it discontinuous, because although the limit does exist here, but f of c here is not defined because it's a hole. So it's discontinuous. Then we have infinite discontinuity, which is like vertical asymptotes in rational functions. This would be discontinuous because the limitations are different on either side, and also because f of c is not defined. And even if it was going like this, even if they were both going to negative infinity or positive infinity, f of c would still not be defined, so it still wouldn't be continuous. Now let's go over removable discontinuity. So removable discontinuity is basically like this. Say we have 3x plus 1 and, I don't know, x minus 2. Say we have like x plus 5 and another 3x plus 1. Looking at this graph, if you're experienced enough with rational functions and limitations, you would understand that these two can cancel out, and we're left with x minus 2 over x plus 5. So what removable discontinuity is, it's basically discontinuity when we can cancel out the point that makes the function discontinuous at some point. So the function would be discontinuous at negative 1/3, right? It's because negative 1/3 is a hole, and we're canceling that out of this function, so that we're left with a simpler function of x minus 2 over x plus 5. That's kind of what removable discontinuity is. You can like remove it from the equation altogether. There's also something called non-removable discontinuities, which is basically the opposite. You can't really remove a discontinuity from the function, even though it deems the function discontinuous at some point. That's kind of the gist of it. Now let's go over our last topic, I promise, which is the intermediate value theorem. So what the intermediate value theorem is talking about is, say we have this interval notation, a and b. Now if f of a is less than f of b, and if they're of opposite signs, so say like a is negative, b is positive, then there has to be a root of c in between this interval. That's basically what it's saying. So let's say we have like this graph. We have 1 and 2. I'm not going to draw this perfectly, but this is the graph of an equation. 1, 2. Let me just erase this right here. The graph here can be represented by f of x, which is x squared plus 3x minus 6. And we want to know why there's a root, or why is there a root in between these two intervals. Well, you can evaluate this if you want, just to double check, but you can actually look at the graph right here. See when f of x is at the x value of 1, we're over here, right? We're at a negative value and we're smaller than f of 2. F of 2 is like, say, around here. So because f of 2 is greater than f of 1, and f of 1 is negative, f of 2 is positive, then there has to be a real zero in between 1 and 2. So that's why. You could also plug it into this equation if you want. You have 1 squared, which is just 1, plus 3 times 1, which is just 3, so 1 plus 3, 4, minus 6 is negative 2. So we have 1, negative 2. If you plug in 2, you get 2 squared, which is 4, plus 6, which is 10, minus 6, which is 4. So by evaluating its coordinates, you can already see why there has to be a 0 here. Because f of 2 is greater than f of 1 and they're of opposite signs. And that's all you have to learn for limits and continuity. I mean, for now.